All right, hi everybody. So here I have a plane in 3D space that I've chosen to orient in this direction, and I have a random point in this space. So if I wanted to find the shortest distance between this plane and this point, what I want to do is, obviously, it'll be the distance that is perpendicular to the plane. So I wanted to show you this angle so that you can see this distance D here, so that you can agree that this is the shortest distance between, everything's falling apart, between my plane and my point. Okay, so right now, actually it's not perpendicular, if I do a better job. So this is the shortest distance between the plane and my point. So now I'm going to just change the angle of the camera so that we can actually see what's happening onto the plane itself. I just changed the angle, but trust that it is still the shortest distance that is perpendicular to the plane, a little bit harder to see from this angle. So if I know the vector equation of this plane, so if I know the vector equation of the plane, that means I know one point on the plane, which I shall call P1. Let me place it here maybe. So I know a point on the plane, and then I know two direction vectors on the plane as well, which this could be one of my direction vectors, so as long as they're non-collinear, then this will define, uniquely define my plane in 3D space. So vector equation of the plane will give me, I will know two direction vectors and a point. So now if I want to use this concept, so very similar to what we did for the distance between two skewed lines. So if I take the cross product between these two vectors, I shall get a normal vector to the plane. Okay, so I will get a vector that is completely perpendicular to both of these vectors, therefore perpendicular to the plane. So if I have a normal vector, again, I can move it in space anywhere that I want. So now you can see it's actually exactly in the same direction as this distance from point to plane that I want to find. So I have a vector in the correct direction. However, I'm just going to move it around so that maybe it's easier to see. So if I place it here, and again, like I did the cross product already, I'm just going to remove these ones. We don't need this anymore. We've done the cross product to find this normal vector. So now that I've found the normal vector, if I find a vector going from point, so let me put away my normal for now, a vector going from point 1, which is a point on the plane, and point 2, which is the random point in space that I'm trying to find the distance. So I'm looking for the distance, orange distance here, the shortest distance from the plane to the point 2. So if I get this vector P1, P2, and if I have the normal vector, if I take the projection of blue vector, P1, P2, onto my normal vector, right? So it's again like the shadow of this blue vector onto this one. I will get, so I'm just going to stick my distance out so that you can see, but I will get hopefully you can see that we're getting that exact distance there, okay? So all I need to do is the vector projection, okay? So I'm getting the distance that I want. So the vector projection of P1, P2 onto my normal vector will give me this distance that I wanted. So essentially that is exactly the same. When you look at the formula, it looks exactly the same as the distance between two skewed lines. So the only difference is here we're taking the cross product between our two direction vectors on the plane. So long story short, the distance between a point and a plane and the distance between two skewed lines is actually exactly the same formula. Slightly different concept, but same idea.